was a pretty great movie.
It was pretty good, but I think this one will be even better.
Really? You sure?
Oh, hello, I didn't see you there. Oh, well, welcome. So this is a special Mr. Webb video. I'm joined, you might recognize Dr. Johnny Webb from our June video, right when school was letting out. But we have a really special treat tomorrow in class, or I guess we're watching it today, but I'm gonna put this up as a teaser tonight for those of you that are subscribers. Is everything okay, Claire? What's wrong? Nothing? You're good? Anyway, so we've been filming a series of geological videos over the last week, and we're gonna splice them all together this evening and play them in class, and then we're gonna have time after for questions and answers. And Miss Maddox's class is gonna join us, and then Miss Whitwell's class is gonna watch the video later. So we're here in this beautiful meadow that I guess was formed by the Deschutes River. Can you let us know, how did this meadow form?
Well, I don't know for sure how this meadow formed.
Well, do you think it was formed by a meandering river?
I would guess that it was from the Deschutes meandering laterally, yes.
Okay.
Because we have a little lake that I think has been modified some called Lake Aspen, but was probably originally an oxbow.
Oh, an oxbow lake?
Yep, that's my guess. But then they turned into the nature center.
What's an oxbow lake?
Well, I'd love to tell you, but we're about to have an airplane fly right over us.
Oh, that's gonna look kind of cool though. All right, see y'all just a second. Uncle Johnny's gonna tell us about an oxbow lake.
Listen.
Oxbow lakes form when meandering rivers do one of two things. They either develop a meander, which is a bend that looks like either the omega symbol or potentially the logo for Lululemon. And when the base of it actually migrates against the other side, the river says, hey, that is a much more direct route. I'm going to just go that way instead. And it leaves the big loop behind, which is, at first at least, full of water. Although it typically eventually fills up with sediment and organic matter and stuff like that. And then other times, during a big flood, you don't necessarily have to have the two parts of it migrating against each other. The water, though, when it rises during the flood, it just shoots across, which is what scientists decided to call it, a shoot cutoff. And if it erodes enough, then after that, the river stays in that course and never goes back to the bend, which becomes the lake. That's all.
Cool. Well, there's a lot more awesome geological content coming your way tomorrow in class. I'm going to upload this, and then I'll upload the rest of the stuff later on. But we're having a lot of fun. It's already Sunday. We're coming back home on Tuesday. So look for it in class tomorrow. Any last thoughts before we go off the air?
Any last thoughts?
Yeah, it's our last video together. Pretty special spot.
You're probably going to see from all these videos that it looked like we were having a really great time, start to finish, and let me tell you, that was the case.
Thanks, Claire, for filming. Ciel, did you want to say anything to the camera? Look at the camera.
Yeah.
What's up?
I saw animals and there were birds, which were owls, swans and stuff. And
Cool. All right.
bye-bye.
Oh, bye-bye.
Bye.
We will talk to you tomorrow.
Hello there.
Hello?
I'm Johnny Webb. I'm
Hello,
Mr. Webb's
Webb.
Dr. Johnny Webb.
it's been reneged. Brother. And we have Ciel, who you've probably seen a lot of. This is Charlotte, my daughter, oldest daughter. Johanna's on my back.
Oh, I was showing June. There's June.
June's over there.
There's Yo-Yo.
We're here in Oregon on the east side of the Cascades. And this is the Deschutes River to my left. We're gonna go for a little hike to see something kind of special along the Deschutes. You'll notice that it is a clear day. Last night was the coldest night yet. It got down below freezing, 28 degrees Fahrenheit. So as scientists, we don't usually use Fahrenheit. So as I've done in the past, I leave it to you to convert that to Celsius. And then it's also worth thinking about why last night, which was our first really, really clear night, was also the coldest. All right, here we go. All right, everyone, we have come to our first and potentially only bridge. But if you look closely, you'll see that it's striped. There's actually frost on the bridge, but it's not covering the whole bridge. And so the question is, why? Now standing on the bridge, and if you look down beneath us, we're faced upstream, meaning against the current. And there's a big pile of debris. It's a log jam we just read about. Apparently back a while back, I don't know, 100 years ago, longer maybe, foresters piled up a bunch of logs in a jam in order to protect the bridge, to create a buffer against other objects floating downstream. And because it's been here so long, silt has deposited around the logs, creating an environment for grasses and bushes and things to grow. And then in the background, further upstream, you can see some cables potentially crossing over. And that is a USGS, United States Geological Survey, measurement site where they measure how much water is flowing down the Deschutes River. All right, we're at Benham Falls now. It's off to the south of us. My daughter's a little nervous about being up on this promontory. Here you can see the river is narrower and faster. That's why they call it a rapids. The question is, why is it narrower and why is it faster? What do you think happened in this part of the river to cause this? All right, it's several days later now, but we're actually pretty close to Benham Falls. They're just over there on the new route of the Deschutes River. We read that the river flowed actually, I think, pretty close to where we're standing now before this lava field took over the landscape and pushed the river out that way. And when it did so, it formed a lake, at least for a while. The lake appears to be gone, but some remnants of it, I think, are just over there, which we caught using our other footage. So standing here on this basaltic flow, it's really crinkly. It reminds, do you go by Teacher Webb?
Mr. Webb.
Mr. Webb of Hawaii, and not too surprisingly, the rocks are pretty similar. This one is full of holes. Those are called vesicles, so we say it's vesicular, and they form when the rock solidifies around gas bubbles. The gases, I think the word is exsolve, it's the opposite of dissolve. I heard Mr. Webb talking a lot about things dissolving. Well, gases are dissolved in the rock and the magma when it's below the surface, and when it comes up, they kind of emerge and become gas bubbles. And that's part of why eruptions can be so explosive.
Did you start the video yet, Claire?
So Claire, from where you're standing, can you see the flow behind us?
Yes, I can see the lake that's behind you, and it's just a little tip of this one.
Okay. Are you ready to start, Claire?
I already started.
All right. Okay.
You'll
Just
have to
edit it.
you'll have to edit it.
So, here we are. When you saw us last, we were out there with a couple trains, and now we are just off the summit of Paulina Peak on the edge of the Newberry Caldera. So I have behind me and Luke, Mr. Webb, excuse me. You can see two lakes. Paulina Lake, I think, is that one. Another one's called East Lake. We've got a really magnificent obsidian flow behind us, in which you can see, not a good idea, June. You don't know where the trail is down there. That is a teaching moment. Never throw rocks down the cliffs. People die that way.
Can you hold
Okay.
that?
So, you can see flow features in the obsidian flow. There are some cinder cones on the inside of the caldera. And we are planning to go down to the lakes because the rumor is there are some hot springs along the shore, maybe within the water. And that's because this area is still geologically active. It's not a dead vent. There is thought to be a magma chamber. What did I read? 2 to 5 kilometers beneath the surface.
Did you say what a caldera was?
I didn't. I thought I'd save the big guns for you since you're the teacher.
Yeah, the caldera is the remnants of a volcanic eruption. That's pretty much as far as my knowledge goes there.
That is correct.
Oh, I got it.
Now,
All right, so we got cut off earlier on top of Paulina Peak. We are now on the shores of this lake called East Lake. And if you can see behind us, the water is bubbling. Can you show that? You see the bubbling water? Oh, she's zooming in. Cool. Anyway, we were talking about how a caldera was formed, and Dr. Johnny Webb is going to illuminate us on that even further. So, sometime in the past, and I have to admit I don't know when exactly it happened, but this volcano, which is now called Newberry Caldera, would have had to have been called Newberry Mountain or Newberry Peak maybe, but there was some extremely large eruption, and this I think it was a shield volcano. I'm not sure if you know what that is, but it erupted so massively, so largely, that it emptied the magma chamber and the whole edifice collapsed in on itself. Kind of how you feel after you really blow it on a test. And that left a fairly large hole in the ground that has since become the two lakes, although part of the floor of the caldera has refilled with more recent flows like we saw from up on Paulina Peak. Paulina Peak. Mm-hmm.
We've got a cinder cone over here that's covered in trees, and so thus not too young because the trees have been able to grow on it. And then this bubbling that Mr. Webb pointed out is because apparently there's still an active magma chamber beneath us that has magma, and that makes the ground really hot, and water that percolates in either encounters, I don't think it actually really encounters the magma itself, but it encounters the rock that's heated by it, and that eventually makes its way back to the surface, giving you a hot spring, which our daughters are hopefully going to get in pretty soon. Stop the video.